and I want to discuss in the light of all these, no pun intended, wave-particle duality. Okay, so a little premature, but I think it's going to be okay. So quantum mechanics always has a little bit of a philosophical flavor to it. Okay, so where do we stand, okay, in terms of light? So classical physics tells us that light is a wave, right? It's an electromagnetic wave. So I think it's worthwhile, even if you have seen it before, because I'm sure some of you haven't seen it before, to derive how you can actually obtain an equation, a wave equation from Maxwell's equation, right? So in a previous tutorial, you looked at the wave equation, right? And it was in 1 + 1 dimension. Okay. And what was the form of the wave equation? Does anyone remember?
Del square f over del x square equal to
Del squared x squared f.
psi.
Psi, okay, sure. Yeah.
Psi xt, psi of xt.
What sign do I put here? Plus or minus?
Plus.
Plus, and then?
1 by c square.
1 by c squared.
d2 d t square psi.
Okay.
Wasn't it
I think it's actually minus.
Yeah.
Anyway, so this was the wave equation where c was the speed, or the phase speed. Phase velocity is sometimes called, although it's a speed of the wave, right? And why did we need a second order wave? Do you remember that? What was the advantage of the second order equation here?
Something related to acceleration.
Okay, anyone else? I didn't tell you that. It was implicit in the tutorial.
It both accounted for like the right word wave and the left word wave.
Exactly, because we found this really nice coordinate system, which was z plus and minus, which was kx plus minus omega t, right? And then if we did this, then the wave equation became this beautiful simple equation. And that meant that the most general solution was a function of a left moving wave and a function, z plus should be, the plus should be down below, left moving wave and a right moving wave. So if we had taken a first order equation, suppose that our equation was, if you can see, this acting on this is 0. So the right moving wave, I think it's a right moving, no, the left moving wave would satisfy this equation, and the right moving wave will follow this equation. But it's only the second order equation, which is given here, which accounts for a wave that is consistent with the isotropy of space, okay? So this is consistent. The second order in a wave equation is consistent with the isotropy of space. Okay? So isotropy is related to the direction. Okay, so it's a left moving and right moving. Here, direction is left and right. Homogeneity has to do with translation. Okay, so let's now go to and derive the wave equation that is inherent in Maxwell's equation. Okay, so the wave equation implicit in Maxwell's equations. Okay, so let me write down Maxwell's equations, and let me just write their more general form in which we have sources, although I will need the sources. So this is the Coulomb's law. Epsilon naught is the permittivity of free space. Then we have divergence of B, the absence of magnetic monopole. Curl of E is equal to minus the time derivative of B. This is Faraday Lenz's law. It's Faraday's law, the negative sign, which is important for conservation of energy, is called Lenz's law. And then we have curl of B equal to mu naught J plus epsilon naught squared mu naught squared the time derivative of E and dt. So this is called Ampere's law with but there's a
Maxwell's
this is a correct.
correction.
Yeah. Okay. So these are quite amazing. The whole subject of studying this equation is one of the most elegant and beautiful things I've seen in my life. So let's
Sir,
derive.
I couldn't hear what Nian said about that last part. You mark with arrow.
Oh,
It's
Nian said that this was
Maxwell's
Maxwell's
correction.
correction.
Yeah.
So this is, let me just this is a bit of history, Coulomb's law, right? And this is no magnetic monopole. I don't know if it has a name attached to someone. And this is Faraday's law. This is the law that we use behind generating power from hydroelectric, but this sign is Lenz's law. And this is Ampere's law. But the addition of this guy, which came from considering capacitors, is correction by Maxwell. Okay.
Are the epsilon naught, mu naught supposed to be squared? I'm not sure.
No, I think they're squared in the source term, in this term, but in this term they are not squared. Yeah. Oh, I see. Yeah, you're right. It's not squared. Yeah. Yeah. I think you're right. Yeah.
So shouldn't magnetic monopoles exist?
You're right. Sorry?
There's nothing preventing them from existing. We just haven't discovered one.
Shouldn't magnetic monopoles exist?
Yeah, I mean, Saif's, answer is the correct answer. There is nothing in the structure, mathematical structure of physics, or to stop them from existing, but we haven't discovered them. Dirac has argued that the quantization of electric charge is an indirect evidence that magnetic monopoles exist. So, at some point we might discuss that. Okay. All right. So thank you very much, Sai, for that correction. Okay. Now let's see how, I'm just going to derive the, wave equation for. I'm just going to derive the wave equation for the B field. You can do it for the E field too. Okay? So what I'm going to do is that I'm going to take one of these equations, this one, and take its time derivative. Okay. If I take its time derivative, then I get d by dt acting on the curl of E is equal to minus d squared B by dt squared. Okay. Now I'm going to assume that my electric fields are continuous enough that I can exchange the time derivative and the spatial derivative. So if I do this, then the left-hand side I can write it as curl of the time rate of change of the electric field. Okay. And then I can go looking for this guy in Maxwell's equation, and I will find it here. And therefore, I can replace that. And right. So when I replace this, I get on the left-hand side curl of 1 over epsilon mu naught then curl of B inside a bracket, and then I'm going to get a minus epsilon naught J. Okay. So this is right. And then I can use one of the vector calculus identities of a vector field, and I should get something like, so this will give me two terms. One of the term will be the gradient of the divergence of B, and the other term would be the Laplacian of B. Okay. And then I will get the source term, and on the right-hand side, I have minus del squared B del T squared. So I'm not in, so let's put the source equals to 0, because we know that magnetic and electric fields can propagate in the vacuum without far away from sources. So we don't need a current. And then the divergence of B equals to 0 gets rid of this term. Okay. So then what we have left is del squared B minus 1 over C squared del B by del T squared, and where C squared is 1 over mu naught epsilon naught. Okay. So this shows that magnetic fields can exist waves made out of a magnetic field whose speed is given by C, and from the measured values of mu naught and epsilon naught, this turns out to be the speed of light. And therefore, Maxwell's equation predicts that light is an electromagnetic wave. Okay. Any question about the derivation?